long, long time ago, somebody said, what if I could take the square root of -1, right? And all his friends looked at him and said, you're crazy. And he said, but I think it's interesting. And of course, there's this number, I, the imaginary number, which is the square root of -1, which finds its way into all sorts of mathematics. It gets applied everywhere, right, down to like circuit wiring for a house. But the guy that invented it, the guy that came up with this, the guy that asked that silly question, he wasn't thinking about future technology. He wasn't thinking about how he could make people's lives better. He was just sort of pursuing something that he thought was really cool.
In 1989, physicists proposed the construction of the Laser Interferometer Gravitational Wave Observatory. Funded by the National Science Foundation, managed by Caltech and MIT, LIGO is composed of two interconnected observatories, one in Louisiana, the other in Washington State. Now, more than 900 individuals are working to achieve what Einstein himself thought impossible.
The sort of inventions that come along once every several hundred years, like the telescope or the microscope, and how that just totally changes human perception of, the universe and our place in it. And it was clear to me that gravity was one of those frontiers.
It takes truly cataclysmic events, tremendous flows of energy and matter and stresses, stars exploding, colliding with each other on basically stellar scales or larger, to produce even the feeblest amplitude of a wave. Right off the bat, you know it was hard. For many years, people thought they would never be detected.
If we're able to detect a gravitational wave, and I think we will, it's just going to be huge, just as big as, the Higgs boson was at CERN.
Once we detect gravitational waves and we make these detectors sensitive enough to detect them regularly, then we detect them all the time. All of a sudden, we're doing astrophysics with gravitational waves. Never been done before.
So with gravitational waves, you actually have sort of the opportunity to look inside, really see the core of a supernova.
Societies are sort of better in general if you have people that are free to pursue things that they find interesting, especially when those things they find interesting are questions about how the world works. And so I know for a lot of us in the LIGO collaboration, right, there's Einstein's general theory of relativity, which sort of has been a wild success, and it has this one little prediction left that there should be waves in this fabric of space-time. We have some indirect evidence that they exist, but nobody's ever seen them actually move stuff before. And so the fact that we're now able to push the edge of technology to a point where we're hoping to see it quite soon, that's exciting, and that's sort of pushing the boundaries of understanding.
At the end of their lifetime, massive stars will undergo gravitational collapse, whereby they will be crushed under their own mass into a compact object such as a neutron star or a black hole. Occasionally, these remnant compact objects exist in binary pairs that orbit around each other. This system emits gravitational waves, and over hundreds of millions of years, the system speeds up and the objects get closer together, eventually coalescing in a cataclysmic event that produces a black hole. We believe that the gravitational waves emitted from the coalescence travel away at all directions at the speed of light. The emitted gravitational waves actually compress and expand space-time as they travel away from the coalescing system. Millions, or even hundreds of millions of years later, the gravitational waves will pass through the LIGO detectors, causing a relative length change of the two arms.
The L of our interferometer is defined by a vacuum envelope, which is a set of tubes that travel 2.5 miles in distance in this L-shaped configuration. At the ends of those tubes are suspended mirrors, which act like test masses. So when the gravitational wave passes, the space-time between the corner and the end station is modulated, that means that the arms appear to change length. So one mirror is getting closer, the other mirror is getting a little farther apart. And so the laser light, which samples this, reads out the changing position of the masses in the corner. And that's the signature of the passage of a gravitational wave. The actual change in the relative arm lengths of the interferometer due to the passage of a gravitational wave is incredibly small. It's just 10 to the minus 19 meters difference in one arm relative to the other. That's 1/10,000th the size of a proton. The idea that you can make this measurement with macroscopic optics and lasers and seismic isolation is quite remarkable, really. So if you were trying to measure the distance between here and the nearest star, Proxima Centauri, it would be like watching it change by the width of a human hair.
So we're going to the end station to see how much power we get out of the fiber that travels from the corner station all the way down to the end station. And then there's a panel, and from the panel it goes onto a table, an optics table, and we have to see how much power goes all the way to the optics table. And we think one of the fibers is damaged or dirty. We're not sure. We're going to first clean it and see if we get more power out of it. If not, we're going to swap it with a spare. And then once we have enough power, we're going to try to do some alignment on the table. I have such a memory of sitting in the class and being like, that's where I want to work. And it's just amazing that, years later, I'm actually here. I always knew that experimental physics was, one step forward, 20 steps back. But coming right out of class where I was, very type A student, crossing things off my list, getting things done, it was a big adjustment for me to learn how to handle being in an experimental environment and not somewhere where the answers are known. So that was really new to me and really exciting. Technically speaking, I also have no electrical engineering background, so that was something new that I kind of dove into here. It's also hands-on, which I like. Sometimes after sitting at a computer for so long, I like getting up and actually moving around and adjusting things. I realized I really enjoyed physics. I liked seeing how math was applied to real-world things. And something like this, that's such a challenge, even if it is just fine-tuning something, just overcoming that challenge is really fun to me.
So we know from quantum mechanics that there are vacuum fluctuations, even in empty space. So we have light comes in from the laser, it gets split, sent down the two arms, it comes back, and it comes back towards the photodetector. But we know that there are vacuum fluctuations coming in from the photodetector, from this direction. And they interfere with the laser, and that is what causes the noise. It's going to be the dominant noise for advanced LIGO that's going to limit the sensitivity. So we want to do something about that.
Where we used squeezed light, and it's a sort of a special quantum state of light to actually improve the sensitivity of the initial LIGO detector. And that was sort of the last experiment we did before we actually tore it down and now replacing it with advanced LIGO. But the same trick, of course, can be applied in advanced LIGO. So as soon as this instrument is working, some people will think, how can we improve the instrument we currently have? And squeezed light is probably one of the options.
What we can do is squeeze them. So we put something in the way of those vacuum fluctuations that are coming into the interferometer. And it reduces the noise in one of these observables, and it increases the noise in the other observable. And so, you know, if we can say at these high frequencies we're limited by noise in this observable, so we're going to reduce that noise, and we're going to increase the noise in the other observable that we don't care about at those high frequencies.
I've made a pendulum out of just parts we found around here just to demonstrate why we use pendulums for seismic isolation. By seismic isolation, we mean that whatever is hanging at the bottom of the pendulum moves less than the ground. So you imagine my hand as being the ground, and if at very low frequencies of my hand motion or ground motion, whatever's hanging down follows the ground exactly. So there's no isolation there. And then as the frequency gets higher, you see that you get this place where the pendulum, the thing hanging from the pendulum, moves more than the thing you're trying to isolate it from. So that's actually the wrong way of seismic isolation, right? That's making it worse. But as you get to even higher frequencies, then you start to see that it actually really does isolate. My hand is moving way more than the thing hanging from the pendulum. Notice how the pendulum at this level is moving a lot less than my hand, and the one down at the bottom is moving even less than the one above it. That's how we keep things still enough we can see the tiny motions that gravitational waves will cause. We had these big seismic transients that we didn't know where they were coming from, and it increased the motion of the ground by an order of magnitude, or at the YN station by more than an order of magnitude. We figured one possibility might be traffic on the road that was 2 kilometers away. So we sat up on top of the roof out there with binoculars. Oh, there goes a truck, and sure enough, there went the signal on the gravitational wave channel. The thing that sets the period between that we're seeing, the signal that we see, or the time, say, between 2 peaks or 2 valleys in the wave, is the axial spacing. It's how much time between when the front wheels run across the bump and when the back wheels run across the bump. So it's the dun dun.
It's a tuning exercise, you know. It's and because nobody's done it before, there's a lot of trial and error. Certainly, one of the reasons I think people come here is you rarely get an opportunity, no matter what you're doing, to put your hands on such a complicated precision machine. You make a connection between moving something and seeing a response, and it's very interesting to be able to do that on such a large scale.
Getting away from just let's do this because we're going to make money on it. To me, that's not really all that satisfying. It's really exciting to work on such a cutting edge science. The other people that I get to work with are so super top notch, you know, just always somebody to look up to and emulate as far as, you know, their integrity and their knowledge and willingness to teach and share. You know, it's just very satisfying to be associated with them.
Line.
Yes.
So if we want to steer institute, we can steer IM 1 and 2 to change angle of this beam.
Right.
While keeping the retroreflection by steering maybe some of those.
Yeah, I agree.
They'll ask you, hey, what do you want to be when you grow up? But they shouldn't stop there. You know, I want to be a doctor, I want to be a lawyer, I want to be an engineer. Yeah, but I mean, what happens afterwards? You know, it's like they just clap and they let you go. Continue asking, how are you going to get there? What are you planning to do to make it? You know, and then help them out.
I think LIGO is unique in that we have to have teams that work together and that are in each other's way, that are very close in many ways, and I think they did a great job early on fabricating those teams.
I think we are pretty lucky because we have a lot of motivated people, we have a good team, and to a certain degree the fact that we're a little bit isolated because our observatory is a little in the desert. That just means more of a community. If you're in a big place, a big university, then it just tends to walk away a little more. Here basically, I mean, you have not a lot of other choice than eat lunch together. You can either sit in your office or in the lunchroom, and then there's not a lot of cafes around. But certainly one reason I stay here is because it's a pretty good team.
There's a broad diversity of people, of academic levels, and there's just very interesting interactions with people every day.
You get to work with people who are extremely talented and extremely passionate about their job, and we're all kind of coming from different places. You know, you have lots of people in construction, people in rigging, technicians, engineers, scientists. We're all coming together for pretty much the same goal.
Well, there's a lot of freedom to work on things that interest you. If you're good at something and get the job done, you're very often allowed to do that.
Until now, we've been deaf to what's happening in the universe, and we're about to turn on our ears. Once we started looking up at the sky with telescopes, we didn't stop doing it. Once we see gravitational waves, that's it. We're never going to stop listening for gravitational waves. So this is the beginning of a whole new timeline. That blows me away, and that is super exciting. To be able to be a part of that is very cool.